We're getting close to wrapping up this angular momentum topic. The curious part is this separation constant and the L and the M values. The L was the angular momentum that we looked at on the periodic table, and the M was the projections from that. So I'm not satisfied until we go over this and prove it. So what I'm going to do is first go back to a drawing that was from the hydrogen atom via the Schrodinger equation. So there's some information there that we can use to help us figure out what the angular momentum L and the angular momentum M is. This is usually not derived, but I want to do it. Let's start with this equation, which is the angular part of the Schrodinger equation as we derive it, and this y represents the theta and the phi. And the phi part is what I want to concentrate on right now, this one right here. As we look through this, we notice there's no phi angles except on this expression right here, this second derivative. That second derivative can be shown to have a solution of negative m squared. Now let's prove that. And why did I choose m? Well, m is going to be a solution to this thing, so we can replace the y with this negative m squared. We can actually replace this whole second derivative with that. 1 over phi, well, y, if we separate out the phi part of that, the 1 over phi comes here. Second derivative of phi with respect to phi squared, this is capital Phi, so this is actually the function and this is the variable. Let's prove that this can be true. Let's suggest a solution for this using an exponential e to the negative im phi. The exponential is unique in that you take the derivative of it and you get that function immediately back. And you have to take the derivative, of course, of this with respect to phi. So, first derivative of negative im phi is that function times the derivative, first derivative of this, which negative I and m are constants. So then we take the derivative of that, which would be the second derivative. We come up with this result where we have a negative im, and that will equal negative m squared out in front of e to the negative im phi. And I can just replace all of this with the negative m squared over sine squared. Let's look at that put out into a different form on another drawing. This reformulation of what we just looked at is from the last video in the playlist, Hydrogen Atom via Schrodinger Equation. That's hydrogen energies number 4. So I strongly recommend that you watch that video, and it'll make sense where this comes from, because we're going to move on from this. So keep this in your sights, and let me bring up another one that's very close to this. I'm replacing the x with cosine theta, which it was replaced before. So this is essentially the same equation, just with different symbology. Rather than the y's and the x's, I've brought it back to thetas and capital theta, and there's no phi function because that's the minus m squared. Now, the first point I want to make is, what values can this m value be? If this is e to the im phi, what happens is that function taken at phi plus 2 pi has to come back and equal this one, because it's a rotational function. So if that's true, then m has to be an integer. These commutation relations are exactly the same form as the spin. So if you haven't done that video on spin commutation relations, then this may not make much sense to you. So I'm drawing on a lot of stuff here because we're getting towards the end and all these pieces are coming together. L squared, which is the total angular momentum squared, is equal to x and y and z. And if we take the LZ times take the LZ and operate on the vector LM, we get back h bar m. Now where did that come from? Well, the h bar is the measured value, which we can run backwards to the magnetic moment. But this h bar is similar to the spin h bar over 2. The m we know is an integer. If we take the L squared operator, then we've got this h bar squared down here, but we're not sure what to fill in here. Somehow it's going to be some kind of relationship with L's, but we don't know what the L relationship is yet, and that's what we're really trying to find. Now it gets pretty messy. Watch if you dare. This is called, by definition, is called the ladder up, ladder down combination operator. This is defined as the L sub x plus or minus the ILY. Now, where did that come from? Well, let's just use it and keep going. If we take LZ and try to commute it with L plus minus, this is what we get. We get LZ, comma, LX plus or minus ILY. All I did is substitute in here for this. Now, what does that mean? Well, if we take LZ and LX, try to do the commutation, then that's going to be plus or minus ILZ, comma, Y. Now remember, we've got all these things over here that we can use, so we might have to come back and use those. This is where we do the commutation operators. LZ, LX, let's see what that is. Okay, that's a I, H bar, LY. Those do not commute, and this is the result of it, or the uncertainty. And then LZ, comma, Y is, let's look over here, LZ, comma, LY is minus IH, LX. So I've substituted that in. Just gets more fun by the minute. LZ commutes with L plus as we just showed up here. And let's see if we can simplify this a little bit. Well, the I and the negative I, those multiply together to give us a plus 1, and the H bar can be pulled out of both of those, and we get an ILY plus LX. And let's see what that is. That's the same as H bar times the ladder up operator. So I can simplify this to be LZ ladder up or ladder down equals plus or minus H bar ladder up, ladder down. Here's where we start. We don't know what this lambda is. This is that separation constant that's been eluding us. L sub z times the vector LM equals H bar M. We already looked at that. We already established that that's where we're going to go with that. This is what we hope to prove. L squared equals LX squared plus LY squared plus LZ squared. Nothing new there. L operator up times L operator down, well, let's just look at them. Okay, this is by definition, that's what these are. Then we're going to square this expression. Lx squared plus Ly squared. Now where did I get plus y squared? I times I is -1 times -1 gives me a plus 1. That's how that Ly squared can be that way. Plus I times Ly Lx minus Lx Ly. This relationship is the same as the commutation for Lx and Ly because we're taking those two together. Actually, we're reversing it, so that's why it comes up to be negative value here. The commutation operator for Lx and Ly equals commutation operator yields, for this expression here, we get a minus I h bar Lz. And if we plug in minus I h bar Lc, that will result in a plus h bar Lz. Lx plus Ly squared is equal to, here's Lx and Ly squared. That's going to be, if we transpose this equation around a little bit, the Lx plus Ly squared is going to equal ladder up times ladder down minus h bar Lz. See if you can do the algebra on that one. So that means L squared equals, and I'm plugging in Lx plus Ly squared, then I've got an Lz squared out here. And keep going, we're going to make it, I'm just sure we are. L squared equals L down, L up, plus h bar Lz plus Lz squared. This minus h and plus h, notice we switched the up-down operators around, which switched the sign. Now we're ready to use the vectors, and we're going to use the vector L comma L. L minus L plus across L comma L is going to be 0. Lz L comma L is going to equal h bar L times that vector L comma L. So if we look at L squared L comma L, then we're going to have, notice this thing drops out, this piece drops out, and we're left with h bar Lz plus Lz squared times the vector. That's that quantity up here without these two guys right there. And then we come down here and see if we can simplify things a little bit. That's going to be Lz is h bar L times the vector Lz squared. Well, if Lz is h bar L, then Lz squared is going to be h bar squared L squared. And if I factor out the h bar squared and an L, I get L plus 1, which is what we wanted to solve. Stare at that a while and see if you can justify it. Of course, you can comment if you don't understand something, but it's all there in blue and white and red. Finally, to round out all this information, L sub z times the vector L comma m, we already went over this one, is equal to that. Now L squared times that's something different. That's what we just played with. Lz with the operator times that vector, let's see what happens to that. If we reverse these, as we're doing right here, then we can, that would be the same as this plus the commutation operator where we switch those around. So let's see how we can do this to apply it to the vector here. L operator with z L m vector plus, okay, all we're doing is just going to use this identity here, down here. This algebra here shows that this operation will, rather than just h bar m, will give us h bar m plus 1 or h bar m minus 1, which is what the ladder operator is all about. So it's the same as if the vector was L, m plus or minus 1. That's a little proportionality symbol. So this shows that the top state has to be m equals L or minus L, and if we're looking at the ladder operator trying to apply to LL, which is the top state, that equals 0. That was used on the last page. I hope this wraps everything up.